So today we're going to continue from Wednesday. We're going to use some of these sine and cosine functions in problem solvings. And maybe one of these problems that'll bring up a question about these reference angles and how we might extend sine and cosine beyond angles in the first quadrant. If angles are bigger than 90 degrees or even bigger than 180 degrees, how do we compute sine and cosine of those? This is going to be an ongoing series of lectures. Kind of unlike the last topic, sometimes we kind of just give one lecture on one topic and then move on. This trig, we're going to tie in a lot of our lectures together, just because we don't really have enough time to really do it all in once. And the way we build on it, we are always going to be referencing material that we've already built up a little bit. So I encourage you guys, as we get going with trig, to keep yourself maybe a little trig sheet. With the information that you want to know, the information that you want to memorize, and encourage you guys to write this down at the top of your homeworks just as a quick reference for yourself. That way you don't have to keep looking it up. You don't have to keep digging through your notes. And the more you write it out, the better you're going to get at it. The more it's just going to become ingrained in your memory if you kind of write out your fundamentals before getting started on any problem you solve. So let's go over the fundamentals we're starting to build up based off of right triangles. So we're drawing our right triangles. And sometimes, a lot of times really, we want to think of these right triangles as being in a coordinate reference frame with this lower left corner at the origin. Not always. Sometimes we'll just be given arbitrary triangles, maybe in a real world situation, if we've got some sort of loading ramp or something to that effect, where we just consider a triangle as a triangle. But in other cases, we want to consider these triangles in some sort of coordinate frame and sort of embedded into a circle. So we can kind of think a circle of going around the top right point there. I'm going to label the sides X and Y, and then the hypotenuse I'm just going to call R, because we want to think of it as a radius. And what should go on our trig sheet right now? So what do we know? We introduce our sine and cosine. So sine is opposite over the hypotenuse, which is going to give me y over r. Cosine is adjacent over hypotenuse. So that'll be x over r. I guess we should label the theta. So our reference angle is in standard position if we were to think of this in a coordinate frame measured counterclockwise from the positive x-axis for positive angles. So we introduced this on Wednesday. I also gave you guys two triangles, which we won't use today, but let's go ahead and list them. So the two triangles you got to memorize. Pi over 4, pi over 4, 90. Has ratios 1, 1, square root of 2. And then our other triangle is our 30, 60, 90. Pi over 6, pi over 3, pi over 2. Short side's 1, long side's 2. Other side, square root of 3. So these are the things we know, things we want to remember for trig. These are almost always going to be helpful to write down, especially as we move into our topics of next week and getting into the unit circle. These two, hopefully eventually everyone will memorize. I think everyone understands sine and cosine. You guys have probably heard the SOHCAHTOA mnemonic device. Maybe we'll mention that next week once we get into tangent. But there's one other thing I want to write down. One other key identity that will come up quite a bit in trig, but it's a little hidden because we didn't introduce it with trig. It's really, we introduced it back with circles and the distance formula. This is perhaps one of the oldest known theorems, is the Pythagorean theorem. Pythagorean theorem is kind of a hidden tool that comes up in trig that sometimes when you're working on a problem, if you think you're not given enough information or something on your formula sheets in terms of sines and cosines, you forget what else we can use. Always remember the Pythagorean theorem might come into play. So that's our cheat sheet. Let's go ahead and keep that handy and take a look at a couple problems before we get started on the quiz. First one's going to be fairly easy. Let's say we have a triangle. And I give you these sides. Let's say one side's 5, the other side's 7. Didn't draw that to scale. This side should have been a bit bigger. And I said, here's theta. And now the problem just says find sine of theta. So one thing to note that sine and cosine are always relative to the angle. I could have labeled this angle, let's call it alpha. And relative to this angle, the opposite side and adjacent side are going to be flipped relative to angle theta. So in standard position, we could always just think of theta as our primary angle if we have a coordinate frame. I didn't originally draw a coordinate frame on this problem, and usually there's not. But even if it were, say, a different size angle, so for example, if we needed to use this triangle here and we had something like a pi/3 show up, you can always orient and flip the triangles a little bit differently so that they are in standard position if you'd like. But this case isn't too bad. Our theta is here, and we want to find sine. But we have a little bit of a problem. So the opposite side is 7. But we do not know the hypotenuse. So if a variable is not given in word problems or even any problems that might involve some sort of picture, feel free to introduce your own variables. And let's go ahead and keep that r for our hypotenuse. You can call it h too if you like h better for the hypotenuse. And so we don't know r. I know sine theta should be 7/r. I know one of the sides. And so the question remains, well, we got to figure out this hypotenuse. How do we figure it out? And so this comes back to our cheat sheet. What else can we use? Well, we're trying to solve for sine. If we don't know sine, sometimes using cosine is going to be hard as well, right? I still don't know r, so cosine's not going to be helpful. And so what is going to be helpful? This Pythagorean theorem. I know that r squared should equal 5 squared plus 7 squared. And now we can solve for r. So r squared is 74. And now r is square root of 74. Here's a question. Do we need the plus or minus? So always remember, going from an equation like this to the next step, we have to apply a square root ourselves. And anytime we apply a square root ourselves, we should ask, do I need the plus or minus? There are certain situations when we don't. In general, we should include it. But in this case, I claim we don't need it. Why should we only need the positive square root of 74?
Primarily because will always be a positive distance.
Sorry, what was that?
Just saying radius will always be a positive distance.
Exactly. We always consider the radius a positive number. It's a positive distance. So let's put a note there for that. So we always want to consider r as a distance. Okay, so let's take a look at another problem, a little bit harder now. And let's say we've got another triangle. I give you x, I give you theta, and let's say this side is 6. And let's say we also say that cosine of theta is equal to 1/3. The problem is going to be to find x. So we know one side length of the triangle, and we know a cosine ratio of the angle. And our problem now is to find x. It's going to be a little bit of steps in this one. So take a look at your cheat sheet. Let's write down all the information we know. We're given cosine. We want to use all the bits of information we can, namely our side length and the cosine ratio. So our first step, if I know that cosine of theta is 1/3, cosine of theta is the adjacent side over the hypotenuse. So x over, and again, we don't have a variable listed there. So let's go ahead and add a variable ourselves. Big skill to understand how to defining your own variables and labeling sides and variables correctly. Big skill for calculus once you get into word problems. So don't be afraid of introducing your own variables and using the algebraic techniques we're trying to teach. But the problem with introducing another variable is, well, now we have two things I don't know. In the triangle, we originally had x, but now I also don't know the hypotenuse. And so this cosine equation says that the ratio of x over r should be 1/3. Does that help us? Well, it's not wrong. It's certainly a true statement we've got written down. However, we now have two unknowns with one equation. So just like we were starting to get into with those exponential examples, when we were finding exponential functions between 2 points, when we were taking a look at some of the examples with arc length and areas of sectors, where there I have two different formulas for two different values, sometimes we have to use more than one equation. Right? Remember, the number of unknowns you have is the same number of equations you need. So we've got two unknowns now. We need two equations. We've got one. Where should our second equation come from? We need an equation that relates x and r with a known quantity, preferably. So you can go back to your cheat sheet. Well, what else do we know at this point? Sine, Pythagorean theorem. Sine's actually not going to help us. And why not? I can compute the sine of this angle. It'll be 6 over r, but I'm not given any other information about sine, what the sine ratio should compute. You're not given that hard fraction of what that number is. So we wouldn't even have an equation out of that. And so let's once again use our Pythagorean theorem. Pythagorean theorem is going to say x squared plus 6 squared is r squared. It's our other good equation. So this is this is like the key step. First two steps in word problems and problem solving in calculus. Key things. Defining your variables and then coming up with the appropriate equations that you will need for your problem is like, you get that far, solving it, most people get pretty good at once you've got the right information down. And this is a good equation. We still only have two unknowns, and they're the same unknowns as the ones in our first equation. So now using these two equations, we can solve for the things we don't know, for both x and r. So how do we do that? Let's go ahead and use one of the equations and then plug it into the other equation. Which one do we want to start with? I always like to start with, again, the easier one. This one's x over r. This one has x squared and r squared. It's going to be a little more complicated. So let's start with equation 1, solve for one of the variables, and plug it into equation 2. Which variable do we want to solve for? It doesn't matter. You could do either one, and you can eventually solve the problem. For the sake of saving a little bit of time, we only need to solve ultimately for x is the goal of the problem. I don't have to find r, though we can if we need it. So if I want to find x, what we're going to do in our first equation is actually solve for the other variable. We're going to solve for r first. Here, let's do it in steps. So we'll have x is equal to 1/3 r. And so r is 3x. The reason I want to solve for r first is because you're essentially kind of solving out that information. You're kind of getting rid of the information of r when you solve for that in the first equation and only retaining this information of x, which I'm now going to stick into our second equation. And now when we stick that in, we'll have x squared plus 36 is equal to, remember your parentheses, so r itself is 3x, all squared. And when we substituted out the information of r, all we're left with in our problem is x's. And that's what we want to find. And so the rest is just a quadratic. Remember to square that 3. Squared. And so we'll subtract the x. We'll have 8x squared equals 36. X squared is equal to 36 over 8. Reduces to 9 over 2. And so x is equal to square root of 9 halves. I'm going to put a question mark here. Do we need the plus or minus? Let's bring up this question again. Any thoughts? Think we need it or no? So the answer is it's a little bit of a trick question. So if the triangle is just a triangle, and you'd even say, even in a real world context, then no. Because x is a distance. However, if the triangle is in a coordinate frame, in other words, we have a Cartesian plane on it with x and y axes, then maybe. We'll see problems like this next week. Or sometimes I could get multiple answers for angles, if we need to solve for angles in the question, or even side lengths. So let's expand upon that just for a second, and then we'll get started on the quiz here. The idea is this. If we draw now a coordinate frame and say we're looking for a triangle, or we're looking for some angle whose cosine ratio is 1/3, with one side as 6, and our angle just based off of the positive x-axis, well, if x is positive, then it would be here. I specifically label the sides as x and y because it lines up nicely with our coordinate frame. Here, x is positive because we're on the positive x-axis. Our 6 is positive, so we're going up positive 6. If we wanted to, we can actually label this point in the coordinate frame. We now have those coordinates. The x-coordinate is square root of 9 halves. I guess we could simplify that to 3 over square root of 2 if you guys wanted to. Let's keep it as square root of 9 halves, since we're not going to be explaining much more about it. And if x was negative, well, what does that mean now? Well, now if we're on a coordinate frame, a negative x makes sense. I can always go negative on the x-axis. So I can have maybe the angle theta was this angle here. And now the triangle that is essentially made, The vertical side's still going to be 6, but because we're going negative on the x-axis, we could apply this negative square root of 9/2. And this makes sense. Okay, I just have a negative x value means we are on a specific direction relative to a coordinate frame. In this case, specifically negative in the x direction. But we always have to check. We have to check in terms of the context of the problem. In this case, what is cosine of theta going to be? Well, we haven't talked about this too much, but we'll get into this and explain this a little bit better next week. We want to extend our notions of sine and cosine beyond this first quadrant. So namely, what happens now is my angles are in the second or third or fourth quadrant. And what's going to happen is we really want to reference the coordinates defined by the terminal side, defined by the terminal point that the angle passes through. And so if we accepted a negative value for x, while it makes sense to have this negative value, we do need to check, is it what we're looking for? Or does it satisfy the conditions that were initially given in the problem? And what would happen if we compute this cosine? The way we would do it is still use this as our triangle, but our x value, our adjacent side is negative 9/2 over, we didn't solve for it, whatever the r value is. And what does this tell us? This is actually a negative value. R is always going to be positive. So the statement we wrote down, R we always want to consider a distance even if we have a coordinate frame. X and Y we want to allow to be positive and negative to give us a relative position. R is always positive though. And so because this expression is negative, it doesn't satisfy the initial problem, namely that I need cosine of x to be 1/3. So the negative solution actually won't work here. That makes sense? Cool. So we'll expand upon this starting next week. We'll talk more about the other trig functions now, and then while using these building blocks of those basic triangles we started, how can we compute sine and cosine for a much more broader array of angles around the unit circle?